Hi, now we're on our last section associated with gravity, and this is going to start off with what do we really know about big G. Now remember, big G is a representation of that constant of nature, and as such, there are a lot of constants associated with our understanding of the universe, and some theories of physics and of that basis of nature try to come up with an understanding of why we have so many constants and why they're related to each other. But at any rate, at some level we want to be able to measure them. And so this is the constant that we looked at before. Notice we have a bunch of decimal places. And here, this 18 that's in the brackets is to indicate what is the what is the standard uncertainty that we have for this thing. So we have, it's 27 parts per million here. And if we look at the next page, we'll see that the actual data that we have for it is spread out all over the place. So this here is the indication of what is the value of big G that we use for measuring of gravity. And these are all the experimental measurements as indicated by time and a nomenclature associated with what group it was associated with it. And it's all basically based upon a number, that's of this value here. And so this is, what the Zurich people measured in 2006. They measured a little bit more than 6674. And then BIPM measured it in 2013, and they got a value that was somewhere in between 6.675 and 6.676. Now, the biggest problem we have, though, is look at these error bars. The error bar is an indication of how well these particular people measured this value. So they measured a value here, but they're saying that chances are 66% of the time, if somebody followed our experimental directions, that they would get a value that was here. Okay, fine. Zurich had smaller error bars, and 66% of the time, if you followed what they did, they would get measurements like this. Problem is, all of these measurements are basically done the same way, and they are all over the place. In particular, I want you to point out the ones with the small error bars. So this one, this one, this one, this one, this one, and to a lesser extent, this one over here. Certainly, these two are in agreement, but this is way out of alignment with this one, or this one, or this one, or this one. They don't make any sense at all together. The only way out of this predicament is if we make a statement that we don't understand what's going on at the small scales that we're trying to measure G from. After all, we're not trying to measure something that is big. We're trying to measure small effects. And that is what we saw what was causing the problems that I've had and others have had in trying to reproduce this experiment. When professional, quote-unquote, scientists are doing it, they have the same problem. Now, part of this, people have been, if you've got a problem in science, you're trying to, you throw everything at it. So, as I said before, you're trying to look at the variation of the sunspot as well as time on the measurement of G. So is there any correlation between big G and something else? That's the first step. And then once you discover that there's a correlation, maybe you can understand if there's a causation. So here are two plots of correlations that we have for big G. This one is just due to time. And the idea of that is if you can compare it to time, then perhaps you can compare it to the Earth's rotation and some effect perhaps from the sun. Now remember, the Earth has certain layers associated with it, and the variability of the time, how long a day takes, is different from day to day to day. So from that, you can perhaps suspect that because of the rotation, that you have some effect being applied to gravity that you haven't seen before. Remember, gravity is a measure of mass, and the gravitational acceleration that we're talking about has an effect in there caused by the gravity of the Earth. Okay, so the gravity of the Earth is going to, affects our measurement of time, and there's some other effects in there that can get into there. Now, another effect that you can take a look at is see if there is some correlation with respect to sunspot cycle, and that's what this lower picture here is about. And what you see is very many more data points are away from the curve. So this curve here is a representation of the number of sunspots that we see as a function of time. Okay, so here's date again, and here's the number of sunspots we have. I don't have the right scale here to show you against it, but here's the gravitational constant here. And again, we're seeing a lot of points that are nowhere close as compared to this one. Well, it's a pretty reasonable sort of supposition that there is a connection between date as well as the gravitational constant, the g. Although there are some points that are kind of far away, like this one is pretty far away. Now, you might say that this one is far away too, but remember, this error bar is pretty big, so it's only like 3 standard, maybe 2 standard deviations away from the prediction. All right. Still, this is our best theory of gravity. Mind you, Newton's idea of gravity is a simplified version of Einstein's general theory of relativity, which we'll talk about later. And there are a lot of verifications of Einstein's theory of gravity. And here's a partial listing of them. And the latest one is gravitational waves. We have actually measured with the LIGO experiment gravity waves occurring because of a collapsing of 2 neutron stars or 2 black holes into each other, and we were actually able to measure that. And on top of that, see that in electromagnetic rays as well. So this is pretty significant stuff. If you have a theory that talks about gravity, and you're saying it isn't like Newton's law of gravity or Einstein's, then you're going to have to be able to explain all these other effects that we see here. So, and for example, the flat Earth, idea that we're all accelerating at, essentially 9 meters per second up on a flat disk, cannot explain all these other things. All right, to continue on, there are other theories associated with gravity. There are tests that you can make for a modified theory of gravity. And what they mean by modifications is that the distance effect in Newton's law or in the appropriate range for Einstein goes down like 1 over the distance squared. It's thought that at very, very large scales that it behaves a little bit differently, and that would help with this problem we have called dark matter or dark energy, I forget which. We'll get into that later. But there is a test that can go along with it, and it's basically looking at the galactic black holes, of which there is a super ginormous black hole in all galaxies that we see, particularly spiral arm and elliptical galaxies. They're 4 million times the mass of the Sun, for example. And the idea has been already tested already, but it isn't precise enough to really test the theory. But the idea works. All right. So we talked about gravity. What good is it? Well, basically Newton's law, universal law of gravity, explains Kepler's law. Remember Kepler's laws, there were 3 of them. And all you need to do is replace Newton's law and you can explain all of Kepler's laws. That's basically what it boils down to. So we continue along and let me remind you what Kepler's laws are, that there is a relationship to the period and the size of the orbit. Newton re-derived this from his gravity law, and from that you're able to measure the mass of a body by some other body orbiting around it. So I have a stellarium for you to work on that you can measure the mass of Saturn by watching how the Galilean moons orbit the planet. So you don't need to be on the planet in order to measure its mass. In a similar sort of fashion, you can measure the mass of the Earth by noting how long it takes the moon to go around us and to know how far away the moon is from us. Remember early on, a couple of lectures ago, I told you how to measure the distance to the moon. And the Greeks are able to do that within about 10%. And so here for t, you put in 1 month. Okay, now you're going to have to put it in seconds, but I'm sure you can make the conversion. And the distance from us to the moon is essentially, half a finger thickness, right? That's the angle. And you know that the moon is about 1/4 of the size of the Earth because of the solar and lunar eclipses. So that will allow you to figure out what the mass of the Earth is. Now you have to go and figure out another way of measuring the mass of the Earth, but at least it gives you an idea. Okay, so you can measure the mass. All right, so here we come up with an in-class exercise for you. I want you to think about what would happen if we set the velocity of Earth to 0. Now, the Earth is going around the sun at about 30 kilometers per second. What happens if you were able to just stop it? What would happen then? In a similar sort of fashion, with the moon, what would happen if you turned off gravity? What would happen to the motion of the moon? Would it go? Keep on going? Would it fall down? Where would it go? Now, these are some interesting things you might want to take a look at, too. Now, assume that these big masses are fixed. They're stuck onto this piece of paper, okay? Now, you let go of the little one here. What's going to happen to it? Where is it going to move next? In a similar sort of vein, if you put down this hockey puck here, where will it move next? And similarly, if you have 2 big masses here, and you have a little mass here, and you flick it, where is it going to move next? And similarly, what's going to happen with this little guy? So, you can imagine this is the Earth, and you drill a hole down from one side of the Earth to the other, and you drop this guy in, what is going to happen? Is it going to go down the middle? Is it going to stop there? What is its motion going to be like? This turned out to be similar to a question that was asked to me when I was getting my PhD. A bunch of oral exam questions like this were asked. All right, this is the thinking experiment that Newton used, and I'd be remiss not showing it to you. Basically, the idea here is that you have a cannon and you're shooting off the cannon with more and more energy as represented by these parabolic shapes that are going further and further out. And he basically thought about what would happen. You can't really do this experiment, but you can think about it. So you launch this cannonball, and it goes, if you launch it with more and more gunpowder, it's going to go further and further away, until at some point it's going to go away at the same, and it's going to fall at the same rate as the horizon falls. Okay, so this is really your horizon. Okay, this is the Earth, and it's falling away from you, right? Because your eyesight goes in straight lines, just as this guy. And so at some point, this is going to fall away just at the same rate as the Earth's distance, or Earth's ground level falls away. And when that happens, you're going to orbit. Right? You're going to go around and around. Now, that gives rise to thinking about things that are in space. If you're going at 8 kilometers per second, you can be in a low Earth orbit, and the way I remember that is, it takes about 90 minutes for something to go around the Earth in a low Earth orbit. Satellites are always in constant free fall. There's gravity there. You might feel weightless there, but that's only in reference to the fact that the scale is also falling all the time. And therefore there's no force between you and the scale. There are lots and lots of satellites around the Earth, lots of space junk as well. And for a geostationary orbit, this is sort of a definition if you want. It's an orbit that goes once around per day. And so if you have a satellite system that is transmitting stuff to Earth, like television stations, I Love Lucy, for example, then all you do is have one satellite here, and you can transmit to all of the United States at one time. By the requirement that it takes 1 day to go around, we can go back and look at Newton's law, or Newton's variation of Kepler's third law. So we have the mass determined, it's the Earth, and that's going to be related to the radius of the orbit divided by the time period. So now we have the time period, and that specifies what the radius has got to be. So 6.6 Earth radii out there, or 42,000 kilometers. Now the escape velocity, that's another term that we want to define, and that is basically what is the velocity that you need to give to something in order for it to escape the effect of gravity. The escape the effect of gravity is at infinite distance, and so if you have something, give something 11 kilometers per second of velocity at their surface, then you will escape Earth's gravity. And then, another in-class exercise for you is if you were to suddenly split the moon into two, what would the orbits look like? And then, some ultimate thoughts here on gravity. Last one. We'll talk about black holes later. There are other forces that are independent of mass. Let's see. The other forces are independent of mass, but this makes the accelerations directly dependent upon mass. That is different than gravity. The acceleration of gravity is independent of the mass of that other body. Okay, and then finally, Einstein says gravity is really warped space-time. And I want to show you now a reduced C simulation, and that will go on for a little while. But,
the video shows photorealistic representations of reduced C scenes. This means that the speed of light has been slowed down from over 1 billion kilometers per hour to a speed of only 1 meter per second. The consequences of this fiction have been restricted to optical effects, and allows us to see special relativistic effects not possible in everyday life. The first scene is a trip down a highway without any relativistic effects. Note the position and orientation of the structures in the desert.
Gotta like the music too. It's kind of scary kind of music. Sort of implying that something weird is going to happen. and something weird is going to happen.
For the next trip, we enable relativistic aberration. As we accelerate, note that the angular compression creates an initial impression of backwards motion. As we pass the sign, it seems to rotate around. This can be viewed as a terrestrial rotation or as angular aberration, keeping the sign in our field of view as we pass it. The back walls of the building are also visible, and extreme distortion is visible on all the objects. Note particularly the sky, steadily shrinking down to the vanishing point. We now enable Doppler shifting. Note that the red desert is blue shifted ahead through the green and red, causing a rainbow effect. As the blue of the sky is further blue shifted, it drains of color. Near the edges of the image, the opposite happens. The sky takes on a reddish hue, and the road is drained of color as the red desert shifts into the infrared. With full relativistic effects now including the headlight effect, the image quickly turns monotone, with objects near the edge of the screen darkened, and the center brightly illuminated.
Okay, now we're going to fly by.
The Terrell effect can be illustrated with this flyby of a cube. Note the orientation of the cube change. Also compare its apparent position with the position indicated on the HUD map. Remember, we are seeing the cube as it was, not as it is.
And that's the key thing. We're seeing the cube as it was, not as it is. So there is an effect of time in there and space. That's why we have to call it space-time, that we have to account for. And that will alter our observations. And this is the even more interesting one. So look at the hub map, which is going to be down here. And this is what we would normally see.
If we instead fly through the cube, the structure's Terrell rotate independently, seeming to turn the cube inside out. Note that even when we have exited the back of the cube, aberration keeps most of it in view.
Here, we're just still inside the cube. Now we're outside, and here in this picture, we're just entering it. Okay, there is more associated with this video later on, but we'll stop at this point.